We'll start in 1 minute. You have a fever?
No, I'm just warm. My hands are really cold. I definitely don't have a fever. I get a temperature check every day. Okay, so that's definitely not happening. I would know. You can't track. Started at 6 this morning.
Do they do temperature checks up at Turner?
No, they do them at Holt. I walk to Holt every day to get a temperature check. Yes,
Oh, that sucks.
it really does.
All right, today we'll be in section 11.4. This is the section on comparison tests. The comparison test. Suppose series of a sub n terms and b sub n terms have positive terms. In part 1, if the b sub n series is convergent and a sub n is less than or equal to b sub n for all n, then the series of the a sub n terms is also convergent. And in part 2, if the b sub n series is divergent and a sub n is greater than or equal to b sub n for all n, then the series of the a sub n terms is also divergent. So I'll just do a sketch of a proof for both parts 1 and 2. The sequence of partial sums S sub n will be for the a sub n terms. So S sub n is equal to a sub 1 plus a sub 2 up through plus a sub n. And T sub n will be the sequence of partial sums for the b sub n series. So T sub n is b sub 1 plus b sub 2 plus ... plus b sub n. So in part 1, we can say that S sub n is less than or equal to T sub n for all n, because we're given that a sub n is less than or equal to b sub n. And we're also given that the b sub n series converges. So that is equivalent to saying that the limit as n approaches infinity of the sequence T sub n is equal to the infinite series of the b sub n terms. So what does this mean? So this implies that this implies the sequence S sub n is increasing and bounded above. Well, what this implies strictly that the sequence S sub n is bounded above. We can also say that the sequence S sub n is increasing by hypothesis. All of the terms in the A sub n series are positive, and so S sub n is increasing. So if this sequence is increasing and bounded above, what does that mean? So by the monotonic convergence theorem, the limit of the sequence S sub n as n approaches infinity is equal to a finite number. And this limit is also equal to the infinite series of the A sub n terms. So I won't write it down since I'm running out of space, but it implies that the infinite series converges. So that's just a rough sketch. For part 2, this time if the B sub n series is divergent and A sub n is greater than or equal to B sub n for all n, we're supposed to find that the series of the A sub n terms is also divergent. Okay, so for this one, we have a role reversal. So this time T sub n is less than or equal to S sub n for all n, because A sub n is greater than or equal to B sub n for all n. So since the limit as n approaches infinity of T sub n equals infinity, so we can say that because the series of B sub n terms has positive terms, and we're told that it's divergent, so it has to diverge to positive infinity. So since this limit doesn't exist, it diverges to infinity. The same is true for the sequence S sub n, also diverges. So we conclude that the infinite series of the A sub n terms diverges. Okay, so let's take a look at this example. Does the series 3 over 4n minus 3 as n ranges from 1 to infinity, does that converge or diverge? So with a little practice, you can acquire sort of background knowledge to know almost by looking whether it should converge or not. So in your experience so far with infinite series, is there anything that makes you think that it has to converge or has to diverge?
1 over n usually converges to 0.
Well, the sequence of the A sub n terms, the sequence of 3 over 4n minus 3, that sequence does converge to 0, but does that mean that the infinite series converges? Not necessarily. We'll review that a little bit later today, but Yeah, so it is true if you identify the a sub n sequence, this is just the sequence that we're adding in this infinite series. So the limit of that does equal 0, but that doesn't tell us whether or not the infinite series converges or not. So when I look at something like this, the terms are 3 over 4n minus 3, I'm thinking that it has to be similar to what the series of 1 over n does. So we saw that series before, the harmonic series. Like I say, the thing that I think about is this series. Do you remember what this series does?
Does it diverge?
It diverges. This is the harmonic series. We showed that this diverges a few days ago. So 3 over 4n minus 3 isn't exactly 1 over n, but the numerator is a positive constant, and the denominator is linear. 4n minus 3 is linear, but it has the same characteristics as 1 over n. The numerator is a constant, and the denominator is linear. Okay, so we're going to use the comparison test to show that this does diverge. So first, I'll make this argument. For n equals 1 to infinity, 4n is greater than 4n minus 3. Are you in agreement? Okay, if 4n is greater than 4n minus 3, then if I reciprocate both sides, the inequality switches directions. So 1 over 4n has to be less than 1 over 4n minus 3. Then if I multiply both sides of this inequality by 3, the inequality is preserved. So 3 over 4n is less than 3 over 4n minus 3. So the series from n equals 1 to infinity of 3 over 4n, if I apply the distributive property in reverse, I can factor 3 over 4 out of each of the terms in that infinite series. So I'll do this in a couple of steps. I can rewrite this as the infinite series from n equals 1 to infinity of 3/4 times 1 over n. But then I can, using one of the properties of series, I can write this as 3/4 times the infinite series 1 over n. So we already saw that this series diverges, and so 3/4 times a divergent series is also divergent. Okay, so this diverges. And since 3/4 times this harmonic series is less than the other series, we can conclude by the comparison test that this series diverges also. Right, by the comparison test. Okay, the next one. Does the series of 1 over n factorial as n ranges from 1 to infinity, does that converge or diverge? Well, if you played around with it for a little while, you could probably make an accurate guess on what it should do. But I'm going to start this way. I'm going to write that n factorial is greater than n squared for values of n greater than or equal to 4. So remember what n factorial is. So we can check that for n equals 4. 4 factorial, this means 4 times 3 times 2. And this is equal to 24. And then when n is 4, 4 squared is 16. And 24 is greater than 16. I won't go through the process, but we could do an inductive argument to show that n factorial is greater than n squared whenever n is greater than or equal to 4. Okay, the terms in the series have the form 1 over n factorial. So if n factorial is greater than n to the second for n greater than or equal to 4, then if I reciprocate, 1 over n factorial is less than 1 over n squared for n greater than or equal to 4. Okay, so the series, if we start at n equals 4, of 1 over n factorial, well, that should be less than the series of the 1 over n squared terms. But we know something about this series, the 1 over n to the second terms, as n ranges from 4 to infinity. We know that this one diverges, or sorry, it converges. Like this one converges. So what's the name for this kind of series?
Telescoping?
It's a p series with p equals 2. So p series, p equals 2. And p series converges when p is greater than 1. So I'll make that note. So p series converge when the value of p is greater than 1. Okay, so by the convergence, or by the comparison test, we can conclude that the full series of 1 over n factorial from n equals 1 to infinity converges. So are you worried about the first 3 terms? Well, yeah, we don't have to worry about the first three terms. So as long as we can omit a finite number of terms until we get to where we need to get, and if we can show that from n equals 4 to infinity that it converges, then if we just add on the other finite numbers, the finite number of finite numbers, we'll still have a convergent series. Okay, so both of those examples were by using the comparison test. We have another comparison test called the limit comparison test. Okay, this one says, suppose the series of a sub n terms and the series of b sub n terms, suppose those series have positive terms. And then it says if the limit of a sub n over b sub n as n approaches infinity is equal to c, where c is a positive finite number, then either both series converge or both diverge. Yeah, the hypothesis of this is that the limit of a sub n over b sub n as n approaches infinity is equal to a finite positive number c. Okay, that's what we're given. So what does this limit mean? So for every epsilon greater than 0, there exists a natural number n such that n greater than or equal to capital N implies that a sub n over b sub n minus the absolute value of a sub n over b sub n minus c is less than epsilon. You might have done a few epsilon proofs in Calc 1. This is what it would mean if this limit is equal to a finite positive number c. This absolute value inequality, the absolute value of a sub n over b sub n minus c is less than epsilon. Without the absolute value symbols, this means that negative epsilon is less than a sub n over b sub n minus c, which is less than positive epsilon. If we add c to all three parts, we get c minus epsilon is less than a sub n over b sub n, which is less than c plus epsilon. And a sub n and b sub n are positive numbers, so if we multiply all three parts by b sub n, on the left we get c minus epsilon times b sub n is less than a sub n, which is less than c plus epsilon times b sub n. Okay, the conclusion of this conditional statement says that if the hypothesis is true, then either both series converge or diverge. So there are two cases. case one, suppose the B sub n series converges. Okay, if that series converges, then the series where we just multiply each of those terms by c plus epsilon also converges. And then we can use the comparison test that we just looked at by the comparison test. The sequence of a sub n terms also converges. Since a sub n is less than c plus epsilon times b sub n. Okay, I'm running out of room. Case two, though, is if the b sub n series diverges, okay, if this series diverges, then if I just multiply each of the terms by c minus epsilon, also diverges. But since c minus epsilon times b sub n is less than a sub n, by the comparison test, the series of a sub n terms also diverges. So I'll squeeze that in here. The series of a sub n terms diverges according to the comparison test. This limit comparison test is, you'll find with practice that you might end up using this more frequently than some of the other tests. So let's try it out on a couple of examples. Does this series, the terms have the form 2 divided by 3 to the n minus 7, as n ranges from 1 to infinity. So we want to determine if it converges or diverges. So that is 3 raised to the exponent n as opposed to 3 times n. So do you think you have an inkling as to what it should do?
Converge.
Do what?
Converge.
Diverge? That's not what I'm thinking, but okay, on this one, if you take away the accessories and think of 1 over 3 to the n, what would the series?
Geometric.
Yeah. So when I look at that and I think of, since I have 3 to the n in the denominator and the numerator is a positive constant, and I'm just subtracting a constant. So I'm thinking of this series as a comparison 1 over 3 to the n. But 1 over 3 to the n is 1/3 to the n. So this is a geometric series that converges. I know that it converges because the common ratio is between -1 and 1. So I'm thinking this ought to converge in the similar way that this geometric series converges. Okay, so we'll apply the limit comparison test. So let's just remind ourselves, if we have two series, a series of a sub n terms and a series of b sub n terms, and then if I compute the limit of a sub n over b sub n and get a positive finite number as a limit, then either both of the series converge or both diverge. So we know that this series, this geometric series, where the terms are 1/3 to the n, we know that this converges. So if we can use the limit comparison, take the limit of the ratio of the terms and get a positive finite number, then we will be able to conclude that this series also converges, because the limit comparison test says they either both converge or both diverge. Okay, so the limit as n approaches infinity, so I'll take the terms from this series, 2 over 3 to the n minus 7, and divide it by 1 over 3 to the n. Then we can rewrite this as, well, if you have one fraction divided by another, that's equivalent to multiplying the top fraction by the reciprocal of the bottom fraction. So this is like 2 over 3 to the n minus 7 times 3 to the n over 1. So we'll do a little more arithmetic here. So in the numerator, we have 2 times 3 to the n. In the denominator, 3 to the n minus 7. Hey, now what? Well, what I'm going to do now, I'm going to multiply this expression by 1. So if I multiply it by 1, I'm not changing the value. But the form that one takes is the key here. So what form should one take if I multiply 2 times 3 to the n over 3 to the n minus 7?
3 to the n divided by 3 to the n.
Yeah, 1 over 3 to the n divided by 1 over 3 to the n. So we're going to make it more complicated before it looks less complicated. So multiply 2 times 3 to the n by 1 over 3 to the n, and divide the denominator 3 to the n minus 7 by 1 over 3 to the n. Then in the numerator, 2 times 3 to the n over 1 times 1 over 3 to the n, that simplifies to 2. And in the denominator, the quantity 3 to the n minus 7 times 1 over 3 to the n is going to be 1 minus 7 over 3 to the n. And then finally, we take the limit. As n approaches infinity, 7 over 3 to the n approaches 0. So the limit is a positive finite number. Okay, so since the limit of the ratio is a positive finite number, we can conclude that the given series converges because we know that this geometric series converges. They both converge, or they both diverge. So put in a little bit of detail here. Since this series, 1 over 3 to the n, converges, so does our given series, 2 over 3 to the n minus 7 also converges by the limit comparison test. Okay, let's try the next one. Does the series, the nth root of n divided by n squared, as n ranges from 1 to infinity, does that converge or diverge? This one might be a little more difficult to think about, but we have seen the nth root of n as a sequence. So it's okay to try something. We have, if you think of this as the nth root of n times 1 over n to the second, you might think, well, maybe I should compare it with the series of 1 over n to the second. Because I know that, so this is just an idea. Well, I know that this series, 1 over n to the second, converges. So if I apply the limit comparison test using 1 over n to the second, maybe something will pan out. So if this is our series of a sub n terms, and this is our series of b sub n terms, then if I apply the limit comparison test, I'm looking at the limit of a sub n over b sub n. It doesn't really matter which one you assign to be the a sub n series and which one you define to be the b sub n series. The limit, if this limit of a sub n over b sub n is equal to a finite positive number, then reciprocating it is still going to have a limit of a finite positive number. But I'm just going to assign this series to be the a sub n series, and 1 over n, the series of 1 over n to the second as the series of the b sub n terms. So we substitute those in. So in the numerator, we have the nth root of n over n to the second divided by 1 over n to the second. So when I simplify this, I'm just going to be left with the limit as n approaches infinity of the nth root of n. That's what this ratio simplifies to. We've dealt with this particular limit already a few days ago. So another way to write the nth root of n is n to, lowercase n to the 1 over n. Starting to come back to you? N's, yeah, well, sure. N to the 1 over n, I'll write it down here. N to the 1 over n is, well, n is e to the natural log of n. So n to the 1 over n is e to the natural log of n to the 1 over n, which is e to the 1 over n times the natural log of n. Which is e to the natural log of n over n. And I'm sort of running out of space, but remember what we did a few days ago? We can write this as e to the limit of the natural log of n over n as n approaches infinity. Or we can just take the limit of the exponent. The way we did it a few days ago is we used L'Hopital's rule to get the limit of 1 over n as n approaches infinity, which is 0. So anyway, this limit is e to the 0 or 1. Okay, so the limit is a finite positive number. So our conclusion about the given series is that it converges because the sequence that we compared it to, the 1 over n to the second series, converges. Okay, so we conclude by the limit comparison test that this series converges. Do you see how that works? Okay, on the next page, we'll just, for a little while, we'll have a short review of infinite series prior to section 11.4. So the entities associated with an infinite series of a sub n terms as n ranges from 1 to infinity are the sequences, the a sub n sequence, a sub 1, a sub 2, and so on, and the sequence of partial sums, s sub n. So S sub n is just the sum of the first n terms of the a sub n sequence. We also saw the geometric series. The geometric series has this form, a times r to the n minus 1, n ranges from 1 to infinity. And geometric series converge if the common ratio r is between -1 and 1. and its sum is a over 1 minus r. So I'll remind you of the nth partial sum. If we were to add up the first n terms from a geometric series, of course that means a sub 1 plus a sub 2 and so on. Do you remember what it simplifies to? So a minus r to the n divided by 1 minus r. So this might be worth remembering. And then when you compute the limit of a minus r to the n over 1 minus r, well, the r to the n terms will go to 0 if r is between -1 and 1. But if r is less than or equal to -1 or greater than or equal to +1, then you won't get a limit as a finite number. Okay, this theorem, if the series of the a sub n terms is convergent, then the limit of the a sub n sequence as n approaches infinity is 0. But the converse to this is not true. So it's important to remember that just because the limit of the a sub n sequence is 0, that doesn't tell you whether the series converges or not. Okay, but we have this test for divergence, which is the contrapositive to theorem 6. And this is a useful theorem or test for divergence to remember. If the limit of the a sub n sequence does not exist, or if it does exist but does not equal 0, then the series of the a sub n terms is divergent. And then yesterday we saw the integral test. So suppose a function f is continuous, positive, and decreasing on the interval from 1 to infinity, and let a sub n be equal to f of n, then the series of the a sub n terms is convergent if and only if the improper integral of f of x from 1 to infinity is convergent. Okay, there's a couple of minutes left. Let's see if we can get started on some more examples. So this first series, the numerator is n to the second minus 2n plus 5. The denominator is the square root of n to the fifth plus 3. So a strategy in a case like this in general. So the term with the largest exponent in the numerator is n to the second. And in the denominator, the square root of n to the fifth is n to the 5/2. If I just isolate n to the fifth, take the square root of n to the fifth and write it in rational exponent form, I get n to the 5/2. And then if I simplify this, I get 1 over n to the 1/2. So what could we say about the series where the terms are 1 over n to the 1/2? We know the answer to this. Does this series converge or diverge? It's a p-series. This is a p-series.
They diverge.
Yeah, the p-value here is 1/2, so it diverges. It's only when p is greater than 1 that it converges. So this diverges. So what that leads me to do is I'm going to use a comparison, or the limit comparison test with 1 over n to the 1/2. So that's what I suggest. This will be the last thing I write today. Use the limit comparison test with this series 1 over n to the 1/2. Okay, that's all we have time for today. Tomorrow we'll go on to the next section, 11.5.